If you've been following along in this video series, now you're ready to answer a few basic problems in graph theory. Let G be a simple graph and M equal to the size of the vertex set. Show that M is less than or equal to n choose 2, and determine when equality holds. Let's start with a notation reminder. N choose k like this, you may have seen written as nck, which is equal to n factorial divided by n minus k factorial times k factorial. And that's equal to the number of k subsets of a set of size n. So n choose 2 is equal to the number of 2 subsets of an n set. Remember that an n set just means a set of size n. And this is equal to the size of the set of all possible edges in a simple graph on n vertices. Therefore, m is less than or equal to n choose 2, and m is equal to n choose 2 when the graph G is the complete graph, Kn. Our next problem says, prove that every path is bipartite. Before we do this proof, let's work out a couple of examples. Here we have P4, the path on 4 vertices, and P5, the path on 5 vertices. Now, what we're going to do is show that these two examples work out to be bipartite, and via the examples we'll get an idea for how to prove it in general. Let's first take a look at P4, and we'll label the vertices 1, 2, 3, and 4. Remember that the definition for a bipartite graph is a graph whose vertex set can be split up into 2 parts. So let me draw 2 parts over here. I'll draw a blob for one part and a different blob for the other part. And let's call these parts something. So I'll call this part X and I'll call this part Y. We want to be able to divide up the vertices into 2 sets like this so that every edge in the graph goes between the sets from X to Y, but not from X to X and not from Y to Y. So let's see if we can do that with our path P4. If I start by assigning vertex 1 to partite set X, then I see that it has an edge that goes to 2, so I have to put 2 in the other side. Now 2 is also adjacent to 3, so that means that I need to put 3 back into the partite set of X, and now 3 is adjacent to 4, so I put 4 into the partite set of Y. Notice that now we've used up all of the edges of the path, and there are no edges that would go in between 2 vertices on the same partite set. So, for example here, 2 and 4 are not adjacent, and 1 and 3 are not adjacent. So we can conclude that P4 is bipartite. Let's see if we can do the same thing for P5. Again, let's start by putting 1 in partite set X, which makes 2 go into partite set Y, and 3 into X, and 4 into Y, and finally 5 into X. So again, we have that P5 is bipartite. Now let's look at the general proof. Let Pn be the path on vertices V1, V2 up until Vn, where the edge set of Pn is equal to the set of all edges Vi plus 1, such that I goes from 1 up until n minus 1. So that's just the definition of our path, and now what we want to do is define a way in which to divide up the vertices of Pn so that we can put them into 2 partite sets and prove that all of the edges go between the 2 sets and not amongst themselves. Define the set X to be the set of all vertices Vi where the subscript I is odd, and similarly the set Y to be all the vertices V sub I where the subscript I is even. When n is odd, our path looks like this, with vertices V1, V2, V3, V4, up to Vn minus 1 and Vn. By our definition, the vertices that belong to set X are the following ones: V1 and V3, and we keep going choosing all of the odd vertices until we get to the end, and since n is odd, we choose Vn. And the other vertices belong to the set Y, so we have V2, V4, all the way up to Vn minus 1 belonging to the set Y. Similarly, if n is even, we draw out our path with vertices V1, V2, V3, V4, all the way up to Vn minus 1 and Vn. And again, we look at what vertices belong to set X, which are V1, V3, all the odd ones. In this case, Vn minus 1 has the subscript that's odd, so that belongs to the set X. And now we put the rest of them into the set Y, V2, V4, all the way up to Vn. In either case, every edge of Pn is of the form vi plus 1, where clearly I and I plus 1 are of different parities. When I say different parities, I just mean that one of them is odd and the other one is even. Therefore, every edge has one end in x and the other end in y, and that is exactly the definition of a bipartite graph. So we've just proven that every path is indeed bipartite. I'm going to continue this problem set in the next video, so see you next time.